Hello everyone to today's LeetCode video, and today we are going to discuss a very interesting question on LeetCode. This is question number 993, cousins in binary tree. We have given the root of a binary tree with unique values and the values of two different nodes of the tree x and y, and we have to return true if the nodes corresponding to the values x and y in the tree are cousins. Otherwise we have to return false, and the definition of cousins is provided here that two nodes of a binary tree are called to be cousins only if they have the same depth with different parents. And we have a note as well that in a binary tree the root node is at depth 0 and all the other nodes are at k plus 1th depth. That means if this root node is at 0th node, this 2 and 3 is at first level, and this 4 is at second level or second depth. Let us look at this example number 1. We have our tree as 1, 2, 3 and 4, and the provided x and y are this 4 and this 3. We can simply see from our diagram that this 4 and this 3 are not at the same level, so one of our condition gets false, so we can simply return false from here. Let us look at example number 2. We have our tree as 1, 2, 3, 4, 5, and the provided x and y are 5 and 4. We can see from our diagram that this 4 and 5 are on the same level, and we also have to check that whether this 4 and 5 have different parent or same parent, and we can see that this 4 and 5 also have different parents, so these 4 and 5 are basically called to be cousins, and we have to return true in that case. For example number 3, x as 2 and y as 3, and we can see that this 2 and 3 are on the same level, but one of the conditions is getting false that this 2 and 3 have same parent, so this 2 and 3 are called to be siblings and not to be cousins. We have to return true only if they are on the same depth with different parents. They are on the same depth but they have a common parent, so we are going to return false in this case. Now, what is the approach to solve this? What we are thinking about? We can think about doing a level order traversal of our tree with, for every node, we can save the level of that node with its parent as well. That means for this one, we can save this one in some data structure as 1 with its level is equals to 0 and with its parent is equals to -1. For this 2, the level is 1 and the parent of this 2 is 1. For this 3, the level is 1 and the parent of this 3 is also 1. And for this 4, the level is 2 and parent is 2. Finally, after doing the level order traversal, we can find out our level of our x, level of our y from that data structure. We can find out the parent of x, the parent of y, and we can check our both conditions that the level have to be same of x and y. That means level of x is equals to level of y, and with that we also have to check that parent of x will not equals to parent of y. If both these conditions are true, then only we have to return true, otherwise we have to return false. So this is a basic level order traversal problem with a slightly change in that we have to save the level and the parent of our nodes in some data structure as well. So let us first look our visualization in here. Let us suppose this will be our tree. Now as we can see that this is our tree, so let us make this tree first. Tree is 1, 2, 3 and this is 4. One of our child of this 2 is 4. Now we are doing the level order traversal. So first we need a queue. Here we are with a queue. Now what this queue is stored? This queue will store a node with its value or with its level and with its parent as well. So this node will store a pair with node, that means node or a pointer to that node, because we want the reference for its children's as well. So node pointer, with that the level of this node, that means a pair of int, and the parent for this node, so parent will be the int value. So this queue will stores a pair of node pointer comma pair of int. This queue will store elements like this. Now for this root we are storing 1 with level 0 and the parent of this one will be 0. Why we are storing the parent of this as 0? Because the values in the nodes are basically 1 from 100 and there will be no 0 in any of the subtree of that root node. So we can find that the parent of this root node will always be 0, or we can just assume that the root node parent is 0 and not the -1. We can think about of any negative number -1 or -2 as well, but we are simply keeping that as 0. Now push these values inside our queue. After doing this, we will have to maintain some data structure that will keep track for every node, that means for every node or for every integer value, because all these values are basically unique to each other. So we can maintain a data structure that keep track for every integer, its level, and level is basically in integer form, and its parent value, and that will also be in the integer form. So we can think about a pair of int. Let us suppose this will be a unordered map that maintains key as an integer value and value as a pair of int. Now pushing that inside our queue, we will have to run a loop until this queue gets empty. While this queue gets empty, first time the queue is not empty, so extract our elements from our queue. The node will be this one, that have references for its left and right child as well. As we can see here, it has references for its left and right child. The level will be this 0. We can maintain some integer variable level named as LEV, and that will contain 0, and the parent will contain 0 this time. Like this. So we have our required 3 values popped out our current front part from our QE. So this will be popped out from our queue. Now we have to save these values inside our data structure, because we want these values after doing this BFS or this level order traversal. So we have to save for every integer. That means for nodes value, we have to insert the level with its parent, like this. After doing this, what we have to do? We have to move on the childrens of our current node. We have to first save these inside our data structure, and here we have node as 1, so this 1 is saved with these values of level and its parent. Level is 0 and parent is 0. Now we have to check if our current node has any left child or not. Any left here? And we can see that our current node, which is 1, have a left node. So we can push that left node inside our queue. Push our left node in a pair of node, that means this node dot left with its level, that means our current level plus 1, this current level plus 1. So the current level is 0. For this 2, the level will be 1, and the parent. Now for this left node dot left, the parent will be this node itself. So we have to insert node. Also we have to check if this node has a right children or not. With that we have to check if this has a right children or not, and if it has, we have to push that right children inside our queue with node dot left with level plus 1, node dot right with level plus 1, and the parent of that node dot left is basically this node itself. So we pushed 2 with value with level as 1 and with parent equals to 1. This is our left child, and we pushed 3 with level as 1 with parent as 1. After doing these 2 steps, we again checked that whether this queue gets empty or not. and we can see that our queue is still not empty, it has some elements. So again pop out our elements, popped out our elements from that queue. Node this time will be 2, level this time will be 1, and parent this time will be 1. For this 2 we have to check if this 2 has some left child or not. It has a left child. Push that left child inside our queue as 4 with its level as previous level plus 1, that means 1 plus 1 as 2, and with its parent as node, and node is this time is basically this 2. Check if this 2 has a right child or not. No, it has not, no right child. So pop out, again check that whether the queue gets empty or not. No, the queue has some elements. Pop out our front element, that means node this time will be 3. Node is 3, level is 1, parent is 1. Again we have to save our information here in data structure. For 2 we have to save level as 1 and parent as 1 in a pair of int. And for this 3 we have to save level as 1 and parent as 1. Like that. After doing this we have to check that whether this 3 has left child or not. It has no left child, it has no right child. So again checked whether the queue gets empty or not. No, it is still not empty, it has one element left. Pop out that element from queue. Node this time will be 4, level this time will be 2, and parent this time will also be 2. Save that information in a data structure. With 4 we have to save level as 2 with parent as 2. Now we have to again check that whether this 4 have its left child or not. No, it has no left child. Check that it has some right child or not. No, it has no right child. Go back to the condition and check whether this queue gets empty or not, and this time this queue gets empty. After doing this we have our information in a data structure, and we can access that information from an unordered map in log and time complexity. So we only have to access our required information from this unordered map, and we just have to check that whether our level is at same level, whether our nodes are at same level with different parents or not. So accessing the information from our unordered map is basically of two types. We can access our information or our key references from an unordered map using this subscript operator, or we can use our find function as well. So what we have to use here, we are using find this time because there might be some test cases where this subscript operator gets failed and return a wrong answer, because this subscript operator returns 0 if there will be no key corresponding the value given to this subscript operator in our unordered map. Let us suppose our tree will be 1 and it has no childrens. It has null left children and null right children. The x will be 2 and the y will be 1. And if we try to save our information using our logic here in a data structure, we will store for 1, we will store parent as 0 and level as 0. Because this one is the only node, and if we try to access the level or the parent of this one, we find that level of this one is 0, parent of this one is 0 using this subscript operator. And if we try to access the level of this 2 from our unordered map using this subscript operator, we find out that the level of this 2 from our unordered map is 0, because this 2 does not exist in our unordered map. So this subscript operator returns 0 for those keys pairs that does not exist in our unordered map, and this will return 0 for parent of this 2 as well. And we can find that this level is equal and parents are also equal. Parents are not different basically, so we have to return false in that case. But how this 0 comes? Because this 2 does not exist in our tree, so we are not using our subscript operator, we are using our find operator to find the level and parent of our required x and y, to tackle these types of test cases only. Now let us code this and check that our idea is correct or not. First, we have to maintain some data structure to find our required level and our required parent for any x and y. So we are storing a pair of int against any integer value, and we are naming this as adjacency. This will store elements as for every node value. This will store level with its parent value. Now for doing level order traversal, we need a queue that will store elements as node pointer, a pair of node pointer with a pair of int. How will this work? This will store for every node we have a level for that node and the value of its parent. Now for root, we are pushing our root with level 0 and its parent is 0. Now we have to move on our queue until it gets empty. We now have to extract our node from our queue, and our node is basically queue.front, and doing this queue.front will return us a pair of node and a pair of int. So we have to find our node, so the node will be queue.front dot first element. So this will be dot first. Our level will be q dot front. Our level will be q dot front dot second, and dot second will return a pair of int. After dot second we have to write dot first as well to access the level. So this will be q dot front dot second dot first, and our parent will be q dot front dot second dot second. We have to pop out our current front element, and now we have to save the information. We have to save the node value. For the node value we have to save a pair that have its level and information of its parent. After doing this we have to check if this node has any left child or not. If it has some left child, that means we have to push that left child inside our queue. We have to push our node left with its level as previous level plus 1 and with its parent as node val. We have to check for right child as well, and if it has a right child we have to push that right child with its previous level plus 1 and its parent value will be node val. After doing this, our level order traversal is completed and we have a complete information for every node, that what is the level of that node and what will be the parent of that node. Now we only have to access that information and check our these two conditions. We are first finding the levels of x and y. So level of x will be, we have to check that if our x does not exist in our unordered map, then we have to basically assign the level of x as -1. That indicates that x is not in our tree. So this will check that if this is not null PTR, that means our x is in the unordered map. If this is not null PTR, that means our x is in our unordered map and the level of that x will be adjacency of x dot second. That means adjacency of x will be this pair and dot second will give the level of that x, and if it is not present then the level of that x will be -1. Level of y is similarly adjacency dot find level will be first not second. Adjacency of y dot first, otherwise -1. And now we are finding the parent of x, and that will be find similarly if this exists in our unordered map, then the parent will be adjacency of x dot second, otherwise the parent will be -1, and parent of y will be adjacency dot find y null ptr, null pointer basically, dot second, otherwise the parent will be -1. Now finally we have to just check that whether level of this x is equal to level of this y, provided with the condition that parent of this x will not equals to parent of this y. Now just check that whether this is running fine or not. We have a mistake here. Let us correct this. We have node defined as tree node here. Push it is running fine, and now let us submit this and check if it passes all the test cases or not. It is passing all the test cases, and it also beats 100% of the submissions as well. And we have more challenges that are similar to this as binary tree level order traversal, and if you are finding any difficulties in this question, you have to first check out the binary tree level order traversal on our YouTube channel, and then came back on this question, and then you will find this question as a very easy question, and you can do this question by your own self, by your own then. Now thank you so much guys, and please like and subscribe to this YouTube channel, and if you have any questions regarding this solution, then please do comment and let us know that if this have any further optimized solutions or not. Thank you so much, and keep supporting guys.